The fourth example for implicit differentiation includes a function which requires both product and general power rules. Welcome to differential calculus. Functions can be written in different variations. One type is explicit, which means a function y is defined in terms of x, like y as equal to negative x cubed multiplied by the binomial 3x raised to 4 minus 2. The second type is implicit, where it is the total opposite of the first. Both sides of the equation contain combinations of variables. Applying these two functions in real-life situations, you might notice that implicit functions are more common. With different variables placed together, the differentiation process in implicit functions need not be exclusive. For two variables, differentiation can be taken as dy over dx, or the other way around, the derivative of x with respect to y. The fourth example looks for y prime of 2x cubed as equal to the square of the binomial 3xy plus 1. Again, y prime is the same as dy over dx. From the right side of the equation, note that the terms are grouped together by the exponent, so the binomial is taken as a single term, and we cannot proceed to distribution yet. Place the constant of the left term aside and have 2 with the derivative of x cubed. For the right term, we use general power rule. So let's begin differentiating. The function then starts with the constant 2 times the derivative of x cubed, which is 3x squared, with dx upon dx. For the right side, the exponent of the whole binomial is placed out, and the binomial is written with its exponent deducted by 1. Then with chain rule, take the derivative of the binomial. Dx upon dx is 1. Then this time, we can distribute d over dx among the terms. So the function becomes 6x squared as equal to 2 with the binomial 3xy plus 1. Then distribute the derivative among 3x, y, and 1. You already know by now that the derivative of a constant is 0. Then we should finish differentiating by placing the constant 3 out of the derivative. The simplified function is then 6x squared as equal to 2 with the binomial 3xy plus 1. Then attach the last term with 3 times the derivative of xy. This last derivative requires product rule. So copy the whole bunch of terms from 6x squared and 2 times the binomial, and also the factor 3. Then take the first term x and multiply the derivative of the second term y, plus the second term y with the derivative of the first term x. The second term has dx upon dx, which can be simplified as 1. Multiply the constants 2 from the left and 3 from the derivative to simplify the function, thus having 6x squared as equal to 6 times the binomial 3xy plus 1. Then the other binomial of x times dy over dx plus y. Since we are looking for y prime, we might as well convert dy over dx into y prime. There are also 6's on both ends of the equation, so cancel them out, and have x squared is equal to the quantity of 3xy plus 1 with the binomial of xy prime plus y. Isolate a term with y prime and take the whole quantity. Divide x squared by the other quantity of 3xy plus 1. With parentheses out of the picture, we can transpose y to the other side and have just xy prime as equal to the ratio of x squared with the binomial 3xy plus 1. Divide x to both sides of the equation, thus coming up with y prime is equal to x upon 3xy plus 1 minus y over x. To come up with a single fraction, take the least common denominator, which is x times 3xy plus 1. The numerator then transforms into x squared minus y times the binomial 3xy plus 1. Instead of dy over dx, let's look for dx over dy this time. Since we are working on the same function, treat it as how we analyzed it earlier. The square shows that the binomial is considered as a single term. Place a constant before the derivative and get 2 with d over dy of x cubed. The other side will have to take the derivative of the whole binomial. With differentiation, the function then becomes 2 with the derivative of x cubed, and that is 3x squared. Then place dx over dy. Now use general power rule on the right and take the exponent 2 as a coefficient. Next is to have the same binomial with its exponent minus 1, and then attach the derivative of the binomial. Simplifying some terms, the left side becomes 6x squared times dx over dy. The right starts with the constant 2 and the binomial 3xy plus 1. Distribute the derivative among the terms, making d upon dy of 3xy and d over dy of 1. The second term then is zeroed out. The next thing is to bring out the constant from the derivative. With the cancellation of one term, the function now is 6x squared with dx upon dy as equal to 2 times the binomial 3xy plus 1. Then the group of derivatives has the constant 3 out with d over dy of xy. Although getting simpler, the derivative requires product rule. So take the rest of the equation as they are, and then expand the term having to undergo product rule. That's with a group of 3 times the first term x with the derivative of the second term y, plus the second term y with the derivative of the first term x. The part with dy upon dy can be reduced to 1, making 6x squared as equal to 6 times the binomial with another binomial of x plus y with dx over dy. We simplify the constants in the right side, so instead of working with separate 2 times 3, we take them as 6, which can then be cancelled out with the 6 on the left hand. So the reduced function is x squared dx over dy as equal to 3xy plus 1 with x plus y times dx over dy. To collect the derivative, we must eliminate groupings first, and that is by using FOIL method. X squared dx over dy remains unchanged, but then multiply the terms on the right, making 3x squared y plus 3xy squared times dx over dy plus x and plus y times dx over dy. Without any restrictions now, collect the terms with the derivative. Having to group x squared, 3xy squared, and y by transposition. The derivatives are equated with 3x squared y plus x. Factor out all coefficients, and then divide the whole function with the group coefficients to have the final derivative of dx over dy as x multiplied by the binomial 3xy plus 1, all upon the trinomial having x squared minus 3xy squared minus y.